can get started. So the talk that I'm going to give today is something of a follow-up to what we saw last week with the presentation from Dr. Ozaki about his Ozaki scheme for using low precision matrix units for high precision multiplication. But whereas his was more of a technical dive into that method, the talk I'm going to give today is going to be more on the practical side for HPC applications. But I, of course, know that there are people who could not attend last week's presentation or maybe did not quite get the point. So I will, of course, begin here with a review of the background and what is really driving this research. So, of course, as part of the FugakuNEXT project, we have to be very aware of the recent trends we are seeing in GPU hardware. This is what the hardware is going to be when we build Fugaku, and so we have to look into the future and see what companies are really going to be making. And the thing that's really driving the design of future GPUs right now is the high demand we see for deep learning compute resources. So deep learning is, of course, very valuable in academia. There's a lot of great research being done using deep learning, training models, applying models to simulation problems. But of course, we are just a small player in the world of computers here in the academia. The real guys with money and the ones who are really affecting the hardware companies are these big AI companies that are coming around, things like OpenAI or Tesla. These are the guys who are going to be driving the market. And so companies like NVIDIA or AMD, when they make a GPU, they have to think about how they can best serve that private market. And because these companies are asking for machines that are very good for training their models and running inference on their models, there's an increasing specialization of computer hardware so that it works well for these tasks. Now, deep learning is, of course, not the same as our standard simulation codes. There is some overlap in the sense that deep learning requires a lot of matrix multiplications to be done. And there are many HPC or simulation apps that also rely on matrix multiplication. But the thing that really distinguishes deep learning workflows from what we do in simulations is that in deep learning, you can actually use very low precision for the matrices involved in your calculations. So what this means is that the hardware companies can begin to specialize what they offer so that they can provide a machine that's very, very efficient at performing these low precision matrix multiplications. So you might see a realization of this on a GPU. It might come with something called a tensor processing unit, or NVIDIA calls it a tensor core. And what these are very specialized hardware that can multiply very quickly and very energy efficiently some very small matrices, like a 4x4 matrix. And they do it with low precision, while potentially accumulating in higher precision. So in the top right here, you can see an example of a tensor core that's available on NVIDIA GPUs. What might happen is you'll have two half precision matrices might come in, and then it will multiply and accumulate that result in single precision. Or you might have a tensor core that multiplies very efficiently to matrices composed only of integers, of 8-bit integers, and accumulates that result in 32-bit integers. So this is the kind of exotic hardware you'll see that is useful for machine learning, or for deep learning really, and will be present on the future GPU hardware. But it's the kind of operation that is a little exotic to us in the simulation world, in your scientific simulations for HPC. And this is a hardware feature that you can't ignore because as I said, this is where the market is. So we are seeing an increased specialization towards making this, the dominant feature of a new GPU. So if you look at some specs, which we saw last week as well, we can look at the A100 GPU of NVIDIA, and we would see that while it had very nice performance for either vector operations in double precision, or some, here, this is the double precision tensor core. It's a matrix multiplication in double precision. If you were to do these multiplications in low precision instead, say in half precision, accumulating in single precision like this, there's a huge increase in performance. This is right here, something like a factor of 15 between there. Or if you use the integers, you would get another factor of 2. And this is a trend that is continuing and getting kind of more dramatic as we go. So if you consider a B200, and actually, I hope you are seeing my mouse. Inoue-san. Inoue-san, 聞こえますか?
Yes.
Yeah.
Mom, can you see the mouse?
Yes.
Okay, good.
I can see it moving.
That's good because I'm pointing. Yeah. So on the B200 GPU, the most recent one, this Blackwell GPU, you can see that actually this performance ratio has increased. So you go from something that has only marginally better double precision performance to something, to something that has very, very nice performance for half precision or integer operations. And now you're talking about a factor of 100 to be considered. And so this is not trivial for us to tap into in the world of simulation science, but we really need to think about, a future machine that has a lot of performance here and less performance here. And we need to think about how our applications can be modified to thrive under these conditions. And okay, so this is a trend that the people who are, working on the FugakuNEXT project are well aware of, and especially the guys at the top. So that early on in this project, when they kind of compiled some wish lists, to ask for the bidding vendors about, what would it take for them to build a machine, they would come up with wish lists that look like this, which are kind of in line with where they expect the hardware to be. So the specs we see, and of course, these are not the real specs of FugakuNEXT, they are just a hypothetical set of specs, but it might be something like a machine that has, over 2 exaflops of performance on its accelerators in double precision, which is a very nice improvement from Fugaku over a factor of 5, but it's really something that will have huge performance in the accelerators for low precision operations. Something, here, this is a factor of 75 between these numbers. And of course, while I say this is a nice improvement to go 2.5 exaflops, we'd like to have such a machine. We're talking about an improvement that, from 2020 Fugaku to FugakuNEXT in 2030, there's only a factor of about 5. And so if you work very hard to port your code to FugakuNEXT, and you do the tuning for the GPU, but you're hitting kind of the floating point peak, then the reward you will get is not so high if you're just trying to rely on double precision operations. So really the hope is that we can start to tap into this low precision power that's there and really up the performance of apps on FugakuNEXT. And I post this slide not just because of this. I mean, this is reflective of what we're seeing here, but also because I want to talk about the memory bandwidth aspect as well. You can see that a hypothetical target for the improvement in memory bandwidth of FugakuNEXT would also kind of be in line with the double precision performance. It's like a factor of 5. And this is because there's, similar, constraints and cost and things like that. We would love to improve memory bandwidth by far more than that, but it's, hard and expensive. And so if your code is memory bandwidth bound, you also might have, as a reward for tuning in 2030, only a factor of 5 speed up over Fugaku, and that would be quite disappointing. And so what we can think, though, is that, all right, we have this low precision hardware emerging, and maybe we can use it for our scientific simulations. And there's going to be a lot of research on how to do this and a lot of development of programming models and, improvements to programming languages, not just from us, but from the deep learning community. So we might hope that also as we tackle this problem of memory bandwidth, using low precision types to speed up, accessing data, that it's going to be easier in the future. We're going to, so if you have a memory bandwidth bound code, a lot of this research is going to be beneficial to you, even if you're not directly trying to use these matrix engines. So in the past, I'm sure everybody has heard many talks about mixed precision in their careers, and maybe you've worked on it and maybe you hadn't. I mean, personally, I have always felt like, if I'm going to change my code to go from double precision to single precision and the only reward is a 2x speed up, it's a little risky because you might worry you get the wrong solution. And then what was the point of that? But now really, I think the timing is right with these trends we are seeing. I think it's going to be a good time to work on low precision changes to your code and doing it in a way that keeps your solution reliable. One last background I want to give is this slide on the basics of floating point numbers, because some of this will come in handy later. So let's remind ourselves that a floating point number is made up of three parts: a sign bit, an exponent, and a mantissa. And we call it the floating point number because we pick the exponent so that the mantissa essentially has a 1 at the start, and then you can store that implicitly and get 1 bit for free. So here's like a diagram of what your single precision looks like. You have your exponent and your space for the mantissa. And what we're seeing recently from the area of machine learning is actually new types emerging. Things, I mean, you can imagine what half precision is, but now it's kind of defined. We have different types like this: half precision with less exponent and less mantissa. You have something like TensorFloat 32, which has the same exponent as single precision, and the mantissa is much smaller though, more like half precision. And this is BF16 is a brain float. Again, a lot of exponent, not much mantissa. So in the past, you might have wanted to experiment with low precision types, and you knew that you call, in your C code, you could have a double or a single, but you might not have had that good programming language support for more exotic types or even a half precision type. But really, this kind of stuff is coming online now, not just, we will have hardware for it and we have software for it. So this will be a good timing for you to experiment with some of these more exotic types. But if you can also, in the past, though, if you didn't have support for it, you might have had to rely on sort of these emulation libraries, something like MPFR, which can emulate an arbitrary floating point type in software. So actually, we will use MPFR for part of this talk because of that capability. So I just wanted to draw attention to this. MPFR can emulate all these types, even if you don't have software or language support for it. Okay, so let's get in. This is the background, and now I want to get into, we're a case study that we did where we are thinking about all these same things about reducing these precision requirements, and is a case study related to electronic structure calculations, which is my background. So there's this particular type of simulation code in the electronic structure area, which is called an LCAO code. You don't need to worry about the details of it. But one of the bottlenecks that exist in this code is that we have one matrix called a Hamiltonian, and from it we want to compute this other matrix called the density. And due to some numerical conditions of this matrix, it's not too sparse. We need to calculate a large spectrum, etc. The most efficient way to do this usually is just to directly diagonalize the matrix. So we have this on the right here. You take it, you diagonalize it, and then you use these eigenvectors, the n eigenvectors which are associated with the lowest eigenvalues, and use them to construct that matrix we're interested in, P. And so this is a bottleneck, and we might think, all right, well, we could maybe try some of these low precision operations and on eigenvalue solvers, on dense eigenvalue solvers. But this is maybe not so trivial to dive into these codes. And of course, there's many different ways to do the eigenvalue solve. So for this case study, we're going to think about something that's even simpler. In fact, there's another way to construct this matrix P that we want from the Hamiltonian matrix, which looks like this. Instead of diagonalizing, we just do a shifting and scaling of the original matrix. And then we follow this short recurrence relationship where you see that we're actually just taking, the previous matrix, multiplying it, subtracting it, adding it, etc. So you can see that this is something that's actually really trivial to implement and dive deep into the algorithm. And also, of course, it maps very well to these tensor cores we're seeing because it's all about matrix multiplication. And essentially the way that it works is that it's taking a spectrum that begins where you have your eigenvalues spread out as they naturally are distributed, and we're pushing them to the value of either 1 or 0 as we go. So it is an iterative algorithm that takes many steps, but when it gets there, you get the same result. And because it's doing matrix multiplications the whole time, it actually can be very, very efficient. But we picked it again because we want to experiment very deeply about what the precision requirements of this operation is. So what we actually decided to do is to implement this using this MPFR library so that we could actually do this with arbitrary floating point types, on real data. And so we, set up this experiment where we're going to have different sizes of the mantissa, both for the matrices coming in, this, this on the left side, we can think for the tensor core, what is the starting matrix you want to multiply? And also on the right side, this accumulation value. And then we look at different measures of error that we would get from what we calculate over the course of this iteration. So zooming in a bit, if you look at the top left, I can explain this in more detail. So if you follow this orange line right here with these orange squares, what's happening is that on the x-axis, this is the amount of mantissa, number of bits we're using for, again, the matrices that come in. So you start with a double precision matrix, but then you convert it to this low precision type, which has a smaller mantissa. And then you do the multiplication and you accumulate it in different size mantissa. So here, that is the different shapes and colors. So this orange square, again, is that we are using this number of bits for the mantissa when we come in, and we're always accumulating with 24 bits, or effective bits. This is the single precision. When we go out, this accumulation phase. So you can see that, of course, that, as you improve the amount of mantissa for coming in, the result gets better, but eventually you're going to be constrained by this accumulation phase. And it's interesting to note that it is, in fact, if we do single precision calculations, we are constrained by the accumulation one. So we can't just switch our program very easily from double to single precision, because according to this gray bar, which is kind of, the error tolerance, we want to get below this gray bar. This is kind of borderline right here. Or if you look at other properties, it's not good enough, really. But if we had a little bit more mantissa during the accumulation phase, we could actually do better than single precision, even if that's, we have a very low precision type coming in. So if you have single precision coming in, but then you had this red line, this red one right here, this would be double precision to accumulate. You see that there's a small improvement. I mean, it's a log scale. It's a vector of 10 or something better. And eventually, of course, if you use full double precision, you have a nice, low result. But what we're seeing kind of that's interesting is something in the middle here. Something like this 37 bits for the mantissa here is actually, if you use single precision and you accumulate in this kind of hypothetical 37-bit, mantissa, you would get an improved result, just like double precision. Or if you use it the whole time, you would get a very, very nice result. So what we're learning from this is that actually double precision is too much. It's too much for what the problem we're trying to solve. But meanwhile, single precision is actually too little. So we're kind of stuck in the middle here where, we wish we had some intermediate type that could support precisely the precision our app needs. Now, of course, we could go to NVIDIA or somebody and say, well, can you make us a tensor core which has a, accumulation in this hypothetical amount, but they don't care about our needs. They're not going to specialize like that just for us. But we'll come back and we'll see exactly how we can take advantage of this later. But I also wanted to show just one more slide first, which shows the same experiment done with a different calculation where we're using a different type of discretion. In this case, you can think of it like if you were doing finite element method, it's a higher order finite element, or you can imagine maybe a tighter grid and things like that. But you see, as the problem changes, we have some problems which are more easy and some problems that are more hard, and they have different precision requirements. And so single precision is definitely out. We just can't switch to that naively. But still, we're seeing this pattern where double precision is giving us way more than we need. And we want to find a way to take advantage of this. So the way that we're going to do that is actually to think about high performance ways of emulation. So here we're using, in the previous experiments we're using this MPFR library where every single operation that's done is done with software emulation, to actually keep track of the individual bits. But the idea is that, okay, if we have an algorithm that doesn't need double precision, it kind of needs something in between, maybe there's like a more efficient and cheaper emulation strategy that would allow us to kind of target that intermediate region and realize savings as a result. We don't need to emulate the full double precision, but we need something that's very fast for emulation. So in terms of emulating these matrix multiplications, where you're trying to get a very nice high precision result with low precision operations, I present two methods here. The first one is called Marketis method, which I think you can get some nice intuition from this method. Basically, they are thinking with this method about precisely this tensor core right here, this half precision coming in, single precision accumulation. And they were noticing that, there's a lot of apps that this is just not good enough for. So how can we improve the solution by doing more operations? So the way this method works is that you'll take your original matrix and then you're going to split it into the sum of two equally sized matrices. It's done like this. You first round the matrix to half precision, and then you take the remainder and round that. So now you have these, you add these together and you get an approximation to the original one. And then when you want to multiply two matrices, you just, expand it out. And, we have this low order term that we cross out. We don't need this. So eventually you can, with 3 multiplications, get an improved solution to what you would get if you just, naively multiply with 1 multiplication on this tensor core. And because it's all these multiplications are using the tensor core, they're all very fast. So maybe you don't mind to spend a few more multiplications to get a good result. So that's the Marketus method. And this is one that you can see is relatively easy for you to even implement playing around in your code. But sort of the best version of this that we have right now is what was presented last week here. It's the Ozaki scheme. The Ozaki scheme, unlike this one, can be applied to any type of precision you have. This is really specialized for these half-precision tensor cores, but this one can be done with anything, even the integer tensor cores. And the error that you get will be just controlled by the number of splits as we say it. So here we split the matrix into 2, while with Ozaki scheme, you can split to 3, to 4, to 5, etc. And the splitting is done in a slightly different way than this, but this can be handled by the libraries that are available. We saw the details of that last week. So essentially you get this, here you're thinking, okay, I have some low precision hardware I want to use to emulate a high precision result. I pick the number of splits I need to get to the precision I want, and then the cost will be controlled somewhat quadratically with the number of splits. So these are 2 methods then that we can try for this emulation, and trying to use them to really get exactly that precision that we want without having to emulate the full double precision result. So this is a savings we could realize in an application-specific way. And then last, I would just highlight on this page that for both of these, we've only talked about Mantissa so far. The exponent is also important, and it's taken care of with some scaling operations. And I won't go into the details of this here, but we can discuss it later if needed. Okay, so let's look at using the Ozaki scheme then for this exact same operations as we saw before. But instead of, before here we're doing, emulation in software with different size of Mantissa, here the X value is the number of splits. It's how many times we've broken up this matrix, and it results in how many multiplications we have to do. And here we kind of see that our hypothesis was right, that okay, what we can do is that we do not need to get the result on the bottom here. So focusing in on the red one, which is again that half precision tensor core accumulating in single precision. If you throw in a bunch of splits, okay, you can get the exact same answer as double precision, but you didn't need that answer. You could have used fewer splits and you could have gotten plenty of accuracy that you needed in all of these cases. So essentially for this easier problem that we're doing, we can see that there's actually a savings that can be realized in terms of the number of splits being less, fewer multiplications, and still taking advantage of these very efficient tensor cores. So then we had to expand, of course, this study, so that people in our field could believe it. So we had to look at things like different discretization schemes. As I mentioned before, you have, if you discretize differently, if you use, say, a more higher order method, the error gets worse. So we will actually see a similar story with the Ozaki scheme, where on the right side, we have sort of the most numerically challenging cases, and the left, the easier ones. And what you would find is that for the harder ones, you will need more splits than the easier ones, but the growth is not so dramatic that you have to worry so much about this. You can pick the splits you need for the case that you are trying to study, and you get the speed up that you can, realize as a result. And also we have to consider the fact that when you use an emulation, an approximation like this, errors always accumulate. So the bigger the system is, the more error that is going to emerge from this, but it actually does not grow so bad from our experiments. So we feel from these results, we have good evidence from these results that Ozaki scheme could be applied to these real practical problems and realize speed up. I thought I would share with you a comparison to this Marketis method again, because this Marketis method is very simple to implement for yourself, with the caveat about the exponent needing a little bit more work. But it's something that you could try as an immediate way to access these tensor cores. And so let's see kind of what happens if we compare the Marketis method with different number of terms, focusing on 3 terms versus the Ozaki scheme. And I'm just zooming in here. And what you see is actually in this chart, the further down we go in a cluster like this, these are the different errors, these are the different systems. The further down we go, the more numerically challenging the system is. And so for the Marketis method, maybe you could focus here. You can see that the error gets worse for the more numerically challenging ones, so that maybe, these easier ones are actually not so bad to do. Maybe you can get away with that. But the good thing is with the Ozaki scheme, we can wrap up those harder cases too, while still taking advantage of this hardware. Okay, so I hope that this talk has given you some interest in using the Ozaki scheme inside your code if you have matrix multiplication there. But there may be some of you who are sitting, with somewhat interest, but thinking to yourself, well, that's too bad because my code doesn't use matrix multiplication anywhere. Or that your code is memory bandwidth bound. So what is the takeaway from you? And in fact, I'm familiar with this feeling because most of what work I have done in the previous years has been on what we call order n methods for large systems. And in this case, we're actually doing something very similar. We're using this kind of algorithm, purification algorithm, this recurrence one with multiplications, but something is different here. In this case, we actually have matrices which are sparse. And this comes from the physics that's involved, where if we have a large system, there's kind of a decay in the elements, so we can approximate our matrix as sparse by cutting off small values. And so most of the code that we do in this case is actually try to write as fast as possible a sparse matrix multiplication algorithm that can have this sort of dynamic filtering of elements. And this is something that does not map at all to the tensor core, because the tensor core is there for the dense matrix operations, right? And even if you could put it on the tensor core, this is an order n method, so it's almost, it surely is going to be memory bandwidth bound. So you're still going to be cut off there. You're never going to get beyond the bandwidth of the machine. And so what is the takeaway I had to think, for the real kind of studies that I'm doing? And what I realized is that actually this tensor core was teaching me something about mixed precision that I never thought about before. Usually we think about mixed precision as something like, well, maybe I will, for this part of the code, I will use single precision, and this part I will use double precision, or something like that, or an iterative refinement. But really the tensor core is teaching us to think about precision in 2 stages. Again, it's that precision that comes in, hopping back, hopping in here, we have one precision that comes in and one precision that's used for accumulation. It's that going out precision. And that these can be different. And we should think about that when we implement low precision operations in our code, even if it's not for the tensor core. And furthermore, our MPFR experiments there had sort of shown that actually our precision is limited by that accumulation phase primarily. It's not so much limited by the going in, it's by the going out. And this suggests to us that there is actually a nice way to improve our sparse matrix operations in a low precision way. And what that is to think, okay, well, we can reduce the precision going in. And this is what going to reduce the moving data from memory, the memory bandwidth cost. It's also going to reduce the network congestion because the messages get smaller. But we will still use the high precision for accumulation. This is really where the ops are done. Everything becomes double precision again. And so as a simple experiment of this, we're doing this, parallel sparse matrix multiplication. Well, every time we gather the matrix, which is then used for the local multiply, we do it in single precision. And then we just run the algorithm as it is. The double precision is used for the accumulation and actually multiplying the local matrix we have. And as I mentioned here, this sparsity is controlled by a cutoff where we say a small value is 0 if it's below it. So if we look in our practical calculations, these are the big systems, the big sparse systems. what we see is if we have the double precision result for the for this gathering, or single precision, this is the mixed precision implementation. It's not pure single precision, it's the mixed one where we're doing only on the in. You see that actually the error doesn't change really at all if your epsilon is big. And then if you start to tighten it, it maybe changes a little bit. And then if you go very tight, you eventually, in the more numerically challenging case, do see a difference emerge. But actually, this is a very acceptable result for the kind of calculations we do. And so this is an example of how, even in a case where you're memory bandwidth bound and you're not using tensor cores, you can still sort of get the idea and try to reduce precision and improve the memory bandwidth of your code. But for the people who are using matrix multiplication and dense multiplication in their code, we have some slides for you too. Because, I hope that these two talks could interest you in thinking about whether the Ozaki scheme would be useful in the code that you have right now. And so what we've done is we've developed a library with my co-authors here, which is located right here, which is kind of what it does essentially is that if you have some CPU code that your standard CPU code is no GPU stuff, it just calls dgem blast. Well, what this library will do is it'll actually intercept all those dgem calls. It will put them on the GPU, and then it will use the Ozaki scheme. In this case, it's an integer version of it, but it will run the Ozaki scheme on your code on those multiplications, and then it will return back the result. So you can very quickly see essentially how this will impact the overall quality of your result at the end. It's not a good way to test performance, but it's just a way to get a hint about whether this is really going to improve things for you or not. And so this code works very well in terms of, you can link to a Fortran code, C++, we have no problem with Python, Julia, et cetera, in our experiments. And the only thing you need is to essentially compile the code here. And then you use this LD preload technique so that at runtime, the SO is inserted and it intercepts your calls. And then through the environment variables, you can control things like the number of splits, the size of matrix before you allow it to happen, et cetera, and run it. So this is a port of the nice work that was done by the developer of this integer scheme, Otomo-san, but it's been extended because now it will automatically be applied to a CPU code when it calls dgem, and you don't have to change your code at all to do this. So I can show you some examples of how we're using this in our field of chemistry. So we have a Fortran code, for example, called NTChem, which has this RAMP2 method implemented in it. And this is a code that very heavily relies on local dgem calls. And so we picked a representative task we want to do with this code. In this case, it's computing some interaction energies between molecules with some particular database and configuration. And actually, we know from studying this algorithm that basically it can be broken into two parts, and both of them rely heavily on dgem. The first one we can call kind of a fitting part, and the second is computing the energy, as they say it. These are both expensive, and they both rely on dgem. And if you read the literature, the people will say, actually, the second part here, you can do this in single precision. There's many papers that will attest to this. But this part, you got to stay with double precision. So we can check that too. We can run this library and automatically apply Ozaki scheme to it, as well as a single precision interception. And you will see, in this case, an error of 10 to the minus 2 is good. This is different units from what we were seeing before, but 10 to the minus 2 is a great error. Anything below that is fine. So we can see that, yes, single precision would work for that. And of course, that we could also, if we wanted to use the tensor cores, that Ozaki scheme is a great way to do it. With something like 4 splits, you're already there. Now, the second part, though, you can see in this bottom one, here's what happened if we run the second part in low precision, having fixed this part to use 4 splits. And you do see that as people attest in the literature, single precision is no good. So in this case, people have been stuck. There's no kind of low precision way to do this part until now. But when you have something like the Ozaki scheme, you can actually be like, okay, I just need 5 instead of 4, and now I'm good. And you can actually improve this part as well too. As another example, this one I want to show because here, 4 or 5 splits. I mean, this is a nice result. 4 splits would translate to 10 multiplications, 5 to 15. So it's a very possible to get good speed up when you're talking about a machine that might have 100 times more performance in these kind of units. But there are some codes which are going to be more challenging. So this is an example coming from what's called plane wave pseudopotential density functional theory code. It's a C++ code. And in this code's case, it needs to call this parallel dgem through scalapack. And this is done to orthogonalize a set of vectors that we have, these trial solutions to an eigenvalue problem. And so we give it a representative case where we want to optimize a unit cell. In this case, you can imagine you have a crystal and you want to sort of know, like, what is the distance between everything in it. So here we have this double loop where we are first computing, what we call electronic structure, some description of the system at a fixed point. And then we compute the stress tensor, which tells us how to update the cell size. We update the cell size, and then we repeat over and over again. So if you look at the errors we have in the energy, in these intermediate, you get all these intermediate energies as we go. You see that, with the Ozaki scheme, with 3 or 4 or 5, it's actually a relatively large error here. The units have changed again, I'm sorry, but 10 to the minus 2 it was way too high in this case. Nobody would believe this result. But if we look at the actual convergence of the cell parameters, actually we can sort of get away with more. I mean, I think we get a very smooth-ish, not too jittery of convergence with the unit cell size. And for the unit cell, actually, I think, 10 to the minus 2 or 3 is fine to do it, to be a final result. So something like 6 splits would be a good way to go in this case. And then you might need to, up your quality for the final energy calculation. But maybe 6, but maybe 7. There are codes that require more precision and some that require less. And so what we can do with a library like this one that I'm showing you here is we can look at their needs experimentally, and then we can sort of project out what we'll need to do in the future. And this is something you can do with your codes too, with this open source library. Okay, so that brings me to the end of the talk. So just to summarize what happened here, we talked about some representative calculations we need to do in materials and chemistry calculations, where we have matrix multiplication as the dominant method. And so we use this MPFR so that we could actually explore in depth the precision requirements and realize that while single precision is not sufficient, double precision is actually giving us more than we need. And this gives us this hope that we can realize some savings through emulation. And then we introduced things like the Marketis method and the Ozaki scheme, and showed how these kind of methods let us target something intermediate there and realize savings, because you can get the precision you need, and if you needed less, you need fewer multiplications. So this is a great way to save computational cost. And then I talked about the things that were taught by the tensor cores in terms of thinking about precision as something that goes in and out, so that we can start to have good discussions and good work being done to target these memory bandwidth bound applications and reduce and allow them to be accelerated on FugakuNEXT as well, beyond the limits of the hardware. And then last, I just wanted to finish by saying, thank you guys for coming to the FugakuNEXT seminars. And, we are working on the application side of things to try to get codes ready. We have core applications that we are focusing on, but we want this to be open. And so if you have an app that you want to run on FugakuNEXT in 2030, you're still working on it, or maybe it's already, a very nice GPU code. We want to include you as much as possible. And this could include things like getting your code included in some of these initial benchmarking efforts, getting you access to test beds so that you can sort of see how your code is going to be. And we can ask your advice about some design choices. So this should be something that is open, and we're hoping to pull in more people beyond just what we have in the core application. So if that interests you, you can, of course, contact me, or maybe Inoue-san would be the best person. Okay, thank you for your time.